Hello, my friends. Welcome back. In today's video, I want to start a new playlist. In this playlist, I want to be talking about FPGA design, right? I want to focus on the architecture, implementation, and optimization of digital designs. So if you do not know any FPGA design, like if you've never coded in any HDL languages like VHDL, Verilog, SystemVerilog, or anything like that, this could still be useful to you because I'll be discussing different design. Like I, for example, give you a design, say, okay, I want to implement this, and then we implement it, and then like we try to optimize it and do everything else on it. And if you already know how to design, so this could be still very useful to you because you can learn how to optimize your code. You can learn about different technique for, how to design a good architecture and implementation, like what's the best implementation and things like that. So a little bit about me, I can only tell you that I'm a digital design engineer and I've been working for more than 5 years in an industrial environment in a company, startup company actually. And yeah, and I did my PhD in the same area. So hopefully I know what I'm talking about. Let's get started. So for the introduction, we want to this is what we want to focus on in the first few videos. We want to talk about the three primary physical characteristics of a digital design, which are basically speed, area, and power. Once you design a circuit, what we care about is that how fast is your design, how big is your design, and when we're talking about the FPGA implementation, that translates to how many lookup tables are you using, how many DSP cores are you using, and then obviously the third one would be how power hungry is your design, right? These are the things that we want to talk about. But for the first few videos, we want to be focusing on the speed of the design, like how fast is your design. There is three different definitions of speed. I mean, depending on the context of the problem, we can have the throughput, we can have latency, or we can have something we call timing usually. And so like based on, the context, as I said, we can discuss these three like throughput, latency, and timing when we talk about data processing in FPGAs. So what is throughput? Throughput refers to the amount of data that is processed per clock cycle, right? And a common metric for that could be like bits per second. How many bits are you processing per second? Hopefully your design is more than bits per second. We're talking about megabyte, I don't know, gigabytes per second, hopefully, depending on the design. And then what is latency? Latency refers to the time between data input, like the data that comes to your design, and the process data output. So how long does it take until I have the output data? And a typical metric for that would be just like time, like took this many milliseconds, this many, I don't know, seconds, or clock cycles, like it took, I don't know, like 10 clock cycles for the data to be processed. And timing usually refers to the logic delay between the sequential elements, right? For example, when we design, sometimes, for example, we design something and we say it doesn't meet timing, right? Let's say someone asks you to design it, I don't know, like a circuit that can operate at 250 megahertz, right? You design it, but it doesn't meet timing. It basically means that the delay of the critical path is, such that it's more than you need a longer clock period, which means like lower clock frequency, so it cannot meet the timing. So we want to be talking about that. So for this video, for today's video, the example that we're considering is calculating the third power of any input, let's say input X, right? The first thing we want to do is to implement it in software and then have the HDL implementation. I want to say HDL is short for hardware distribution language, right? I will be coding in SystemVerilog, which is like super close to Verilog. But but once you get the concept, you can do the same thing in VHDL if you're a VHDL guy. Anyway, and then once we have the HDL implementation, we want to head for optimization. Again, the first step is to focus on speed. At least, I mean, I'm not saying that speed is the most important thing. It really depends on the design of what you're designing for. But speed is obviously very important. So I want to focus on speed. So let's get started. We want to do the third power of input x. So input comes in, we want to calculate x to the power of 3. In software, it is super easy because it's a FPGA course, right? I don't really want to like code it in Python or anything. I just like write it here, right? So I'm just going to go x3, for example, that is equal to 1. And then we can go for, I don't know, I0, I less than 3, then I plus plus, right? And then here you go, x3 would be x times x3. So this is a recursive algorithm, right? The first time x3 is set to 1, and then when you come to this for loop, it loops 3 times. The first time it's 1 times x, which is x. So now x3 is x. Second time is x times x, which is x2. So x3 is x2 now. And then multiply that by x3, you get x3, which is the third power of x. Super easy. In today's video, I want to just implement the same algorithm, what we see here in FPGA, right? I want to give you the RTL code so we can see how we can do that in RTL. And then probably in the next video, but I don't know, we'll see how we go time-wise in the next video, but probably like very likely, we will be optimizing this. Okay, I disconnected my pen, so this thing popped out. I don't need this anymore. Anyway, let's get started. So as I said, I want to code in SystemVerilog. So I created this design here, this file in here. Like I created this file, call it power3.sv for SystemVerilog and power3 test bench for SystemVerilog. These are empty for now, but we're gonna start coding and see how that goes. Okay, let's get started. Okay, so my coding style could be a bit different. When it comes to coding, I might have a little OCD, might be a little OCD in the, you will see what I mean. Anyway, let's get started. So I'm just gonna go time scale 1 picosecond, 1. Yeah, that's good. And then we go default net type is none. And then we can get started, right? I usually like to have a header here as well. Just do this. And for them go file, give it the file name, power3.sv, and it just like provide a very brief description of what they're doing, implementing the third power of a given input. So that's what we're doing, and just like align these. And then we go here and just close that. Okay, sounds good. And now we can start actually coding. So module, we're gonna call that the power3, right? And we want to define a parameter for that as well. So I'm just gonna do this. Okay, my battery is dying. Just gonna plug it in quickly. Okay, there we go. Let's silence this. So one parameter I want, I'm just gonna define it here. Parameter d width for data width is 8, for example, right? Don't really need this either. And this is how I like to code. So parameter d width is equals to 8. This is basically the width of my input data, right? And then when it comes to port definition, I just go input wire clock. I want to have a clock, input wire I valid. This is my style. Like they go I valid, which means like input is valid, right? And then I want to go input wire. Well, this one is a bus, so that would be d width -1 down to 0. And then I'm just going to call that a data. And then output logic. And I'm just going to call that O valid. So this one goes up when the output data is valid. Like I'm done calculating the output and it's like valid. It can take the result. And output, obviously, logic. And this would also be a boss. So this is the output. So when you multiply, I don't know, like an 8-bit number, 2 8-bit numbers, the result would be 16 bits and then like another 8. So like the length increases. I'm just going to go 3 times. It's probably not very accurate, but you get the idea. Divid's -1 down to 0, and this is O data, right? And here my OCD kicks in now. These needs to be aligned. Well, the tool is not going to say that you're wrong, but I just like doing this because it's clear. Like I can see what I'm doing, and when I need to debug my code, it's just much easier. Okay, so these are my input ports, right? And now we can start coding here. I want to go logic, and I want to define a 2-bit counter. The way I want to do that is that I want to count how many times I'm multiplying the input number by itself, right? I need to do that 3 times. I only need 2 times. So this is going to be a counter to count how many times I'm multiplying a number by itself. So I'm just going to call that counter, right? CNTR. Then once the output result is valid, what I want to do is that I want to go assign O valid, right? So O valid is 1 when the input is processed. So when basically that means when counter equals, so it's 2 bits. So I'm just going to go 2 t plus 0 0, or you could just put 0. I like doing it this way because again, it's 2 bits here, it's 2 bits here. It's everything is super clear what's going on, right? So if that condition is true, then one tick B1, which means O valid, is set to high. And if not, then it's set to one tick B0. We set it to 0. That's good. And now let's start with the actual statement. Like this is like where we do the calculation. So always flip-flop. And we can say at positive edge of clock, right? So you go pause edge of clock. So every time that you have a positive edge of the clock, you want to do something. I'm just going to call that power calc. Just the name of my process is like power calculation, power calc for sure. And then we go here and we say if I valid. So if the input data is valid, then begin, right? What do we want to do? If it's valid, then I'm just going to vote counter is set to bit. We want to set it to 2, right? Because if the first time it's 2, the second time it's 1, and then the third time it's 0. So we're going to count 3 times. So when input is valid, I'm setting the counter to 2, and then I'm just going to go O data is set to I data, right? This is the algorithm that we had. If you remember, like I can bring this up here. So X3, which is like the output here, is set to 1, right? And that's what we're doing. So it's same thing here. So because like in that code that I showed you, we're looping 3 times here. By setting it to I data, I'm just saving us 1 loop. But anyway, like this is cool. So that's it. And if not, if that's not the case, right? So I'm just gonna go and else if all valid, right? All valid equals 1 TB 0, then right, that's fine. Again, and event. So what do we want to do here? We want to go counter is counter minus 1 TB 1. So we're decrementing counter, and then we go O data is O data times I data, right? So let's see what's happening here. Let's say align these, so these fours are aligned. So what's happening here is that the way this works is that iValid comes in, right? And I'm just gonna add here. This is a pulse, right? So for 1 clock cycle, it goes up and then it's down. And then when the next input data comes in and when it's valid, then it goes up again and comes down in the next clock. So it is a pulse, right? So once I design it, it's like this. I say, okay, like this is my specification. This is how I want my circuit to work. Then I'm saying if iValid is 1, which means, okay, there is a new data on the bus, then counter is set to true and O data is I data, right? Else, which means, okay, now the counter is true, data is valid, let's do the calculation. If O valid is 0, right? And if you remember, we did it up here, the counter is O valid is 0, while counter is not 0. When counter goes to 0, O valid goes to 1. So while the output is not ready, then keep decrementing counter and keep updating O data, right? This is how it works. Super easy. Yeah, that's pretty much it. This is the design that we have. This is a recursive algorithm. And as you can see, it takes probably 3 clock cycles for this to complete the design. We can have a test bench for that as well. We can test if it works properly or not. Here we can just go take time scale, go 1 picosecond, 1 picosecond, that's fine. And then we can add the default net type to none as well. And then we go module. Okay, we go power 3 test bench, right? And then like we can start coding, right? I didn't do this. That's set to none, right? So that's set to none, and then we go here, and then we can start coding. Let's get started. We can go local param, right? HCCL, that equals to, let's say 5. It's half of the clock cycle, right? You can just go half of the clock cycle. And then again, local param, how many samples do we want to pass through, right? It's our test bench. Let's say we want to just go number of samples, right? And we set that to, I don't know, 9 samples, for example. And then we can just go do some signal declaration. I'm just going to go integer TB state. So that would be the state of my TB because it's going to be a state machine, right? And then I'm just going to go integer TB counter. You'll see in a second how I'm going to use this. And then the integer encounter. So TB counter, I use that to like toggle between the like different states in the state machine and also count the number of samples probably. And encounter is like the counter that keeps tracking of like how many times I'm multiplying the number by itself. So we want to set it to 3, right? And then obviously we have registers, which is clock, right? And I'm like, we can do this too. Like we can just initialize this to 0, right? And then we can initialize our clock as well. So clock is set to 0, and we want to have like a register. We'll call that reset, and we set that to 0 as well, or we can set it to 1. Doesn't matter really. What matters is how you use this in your TB, right? Okay, so now that we have like we declare their signals, then we can just go like and do the clock and reset generation, right? So I'm just gonna go initial. I don't really need the begin thingy. Just go time format, I think, if I'm not wrong. -8 0. And then clock here, and then 7. I'm just gonna put up here. And then I'm just gonna go always. There is no at. I just want to keep doing that constantly. I'm saying wait for HCCL, which was my half clock, and then change the clock, right? So clock equals to 1 take B 0, right? And then I just basically want to do the same thing here, and then clock goes to 1, right? And we can do something else here. We can go initial begin and then here we go wait for HCCL, and then reset is set to 1, right? Wait for another HCCL, and then set reset to 0. So I'm just gonna copy this line, bring it down here. So this part of you probably don't care as much because I'm just like writing a test bench. If you don't know how to write a test bench, then sure, yeah, watch this. If not, you can fast forward through the video. But I would highly recommend you watch this because it's important. Like when you start writing the state machine, then you want to know what's exactly going on. And I'm like, okay, now we have everything and we can start like bring our design here. So I'm just gonna go logic, valid, and then what else do we need from logic? Full valid, right? And then we want a just next line, local param w width of the data. We just kind of set it to 3 because with 3 we can go from 0 to 7. So we have like good range of numbers, so we can like calculate the third power easily, right? If we go to like 5 bits, 6 bits, then we need a calculator to do that, like to verify the result. But anyway, so I'm just gonna go logic, and I think when we designed it, we said the output is 3 times bigger than the input, so we're gonna do the same thing, 3 times w minus 1 down to 0. And that would be data out, or data doesn't really matter. Don't forget the semicolons here. And then logic 31 down to 0, just go call that u. And this is a random number. So I'm generating a random number, a 32-bit random number, and taking the first, like the lowest 3 bits of it, and use that as my input data, right? This is what I want to do. So we have this, and now it's time to bring our module. So I'm just gonna go power 3, right? Not TB, but power 3, and then we'll go get it the parameters that it had. So that data widths, right? The data widths that we had was W here. It's such a W. And then we go DUT, short for design, under test, and power 3, just like any name that you want, any descriptive name probably that you want. And then we can go the clock because we had the clock. And well, we can just give it clock here, comma, dot we had iValid if I'm not mistaken. So let's do this here. And I'm just gonna give it the iValid signal as well. And the next one we had was iData, right? And here, as I said, I'm just going to give it u w minus 1 down to 0. So this is what it's going to be. And then what else did we have? So we did clock, iValid, iData, OValid, and OData are the remaining two that we need to do. So that OValid would be OValid, and then that OData is my data out now. Right, and so let's just like bring all these perfectly aligned. Anyway, so that's that, and now we want to design a controller, right? So I'm just gonna go always flip flop, right? At so brackets paused edge of clock. What we want to do is begin. Then let's just give it a name, main process or main controller, whatever you want. Oops, what's happening here? I'm just gonna do make process, and so begin end obviously, and then here we just go if reset begin, and so if reset is happening, what I want to do is to go TB state is set to 0. I want to be in the first state, and TB counter also goes to 0, right? And I want to set my end counter to 3. If you remember, I said like the end counter is the thing that counts how many times we are like multiplying, right? And if it's not the reset, then what we want to do is to go and those begin end, and then here we go case, right? We'll go case PB state. Want to like consider it's basically like a case statement, right? It's same as if, but it's much easier, right? Harder people like it this way. And so just go end case once that's done. And so when this happens, then what we want to do is to go case 0, because like we set it to 0. So now we have to define what we do at case 0. So we go begin end. And what we do here, I'm saying if TB counter equal 0, right? Begin end, right? So if TB counter is 0, which is 0, then I want to display something. I want to display, and I want to go curly brackets percentage 5t to get the time, and be like gate TB, like doing my test bench, and waiting for a few clocks before I'm running the simp, for example, right? You can totally skip this part, that's fine, but I like my test bench to be descriptive when I see it. And so now I want to go TB counter is, I want to update that, right? I'm going to go TB counter is, and I want to use this style of coding. If TB counter equals 3, right? Then 0, otherwise TB counter plus 1. So I just want to wait for like 3 clock cycles, right? That's what I do. Is a TB counter, is it 0? Is it 3? No, it's not. So keep incrementing the TB counter. When it hits 3, it's 0, right? So I want to do the same thing here. They like TB state. Just move that. And basically you want to go like copy this, get down. Oops. What's happening? So if TB counter is 3, right, we set TB counter to 0, and we want to go to the next state, right? So if it's 3, then that would be TB state plus 1. Otherwise, stay where you are, which is the TB state, right? So it waits for 3 clocks and then goes to the next state, which is state 1. Now, what do we want to do here? So this is state 1. Begin and here we can go, the first time we were here, we can just go display. Again, you don't really have to display anything. I'm just going to copy this first part here and be like, what we're doing, sending random data to the module power 3. So now we're like, we want to send input data to our module to calculate the result. So every time it comes here, I want to go iValid equals to 1 bit 0. We set iValid to 0 every time. If we have to change it, then we overwrite it. Now I want to go if TB counter, right, is less than number of samples. We want to like count like, I don't know, like 9 samples. We said, so if it's less than that, then begin end. So if it's less than that, what we want to do is to go if end counter equals 3. We set it to 3 in the beginning. So when it comes here, it is already 3. So what we want to say is that to begin and what's happening here is that I'm just going to go do equals $sign random, right? I generate my random number, and here I'm just getting the least significant bits of it and send it to, by the way, I need to do this, sorry about this, and sending it to like iData, right? So this is the first thing I need to do. The next thing I want to do is to go our valid is 1 bit 1. We need to set that to 1 as well. And the other thing we need to do is to go TB counter is TB counter plus 1 bit 1, or just 1 here would fit. So if end counter is 3, right? So every time we want to give it a new input, we want to set it to 3, so it loops 3 times. And every time I'm incrementing the TB counter by 1, so I'm just counting in sample times. And every time new data comes in, iValid goes to 1. And next time we come here, it sets it to 0. So that is implementing the pulse behavior that I told you about. Now, so that's it. And then we can just go here and be like, end counter, we need to decrement end counter, right? So end counter, these end counter -1, because it's set to 3. Obviously, we need to decrement it so that we know what's going on. And here we go, if end counter is 0 now, right? But 9, but 0, then begin. What we want to do here now is to go end counter is 3. We want to set it to 3. which makes it ready for the next one. And then here we go and else begin, and which is like if the TB counter, like we've counted in number of samples, whatever, like in this example, 9 samples, then we want to go TB state is TB state plus 1 and TB counter is 0, right? That's it for the second case, which is case 1. And then we can do the third case, right? Which is case 2. We go begin. And what we want to do here is basically say, I don't know, like wait for a few clocks until it's done. So we can just go here and copy this probably. And then bring it back. So if TB counter is, I don't know, like we can wait for 10 clocks. It's 10, waiting a few clock before ending the SAM, right? And we can also say TB counter is 0, right? And TB state is TB state plus 1. But if that's not the case, all we need to do is just to increment and I will begin, and then here we go TB counter. This TB counter plus 1, right? Okay. And then, so that's that. And then finally, it's like the end of a simulation, right? So we go, default for the case is begin. And I'm just going to copy this and put this here. And I might go, don't need that. So I just go \n sometimes, and then copy this, and then here would be, I don't know, end of simulation, and then we can just make them of equal sizes, make a look at. Okay, that's it. That should do this. And so we have our design. Make note that like there is no optimization yet. I just implemented the design, and here is the test bench. So we want to make sure that it's working now. I don't have Vivado because like I'm recording this on a Mac, so I don't have Vivado on here. I have to run the same code on my Windows machine and get the result and get back to you about it. So as you can see, the iValid signal goes up 1, 2, 3, 4, 5, 6, 7, 8, 9 times, which is like the number of samples that we want to send in. And the OValid goes up 9 times, right? And so the first time the input comes here, it's 4. And then as you can see, it takes 1, 2, 3 clock cycles until GoValid goes up. And the output is 64. Sounds good. And the next time input comes in, it's 1. So the output is 1. Again, the third one is also 1. So we also get 1. Then the fourth one is 3. And as you can see, we are setting it to 3 here. 3 clock cycles after that, we're getting 27. And then 5, we have 125. And then like again 5, so we have 125. And again 5, 125. So like 1, 2, 3. 3 times you're sending in 5. And then we have 2, we get 8 for that. And then 1, and then we obviously get 1. So it's working properly. It sounds good. So this is the bare minimum design. Like this is just basically the equivalent of what we saw in software with absolutely no optimizations. In the next video, I will be showing you how we can actually make some changes to this to speed the design up. Because right now, our input data is 3 bits, right? And we are processing 3 bits in 3 clock cycles, right? Which is not really efficient. In the next video, I will show you how we can improve that. Thank you for watching me. Please let me know in the comments if you had any questions. I'll be more than happy to answer the questions. And if you haven't already, please do not forget to subscribe to my channel. It helps me a great deal.